In this video, we're going to discuss shockwaves. So imagine that you have an airplane traveling through the air. So whenever we're traveling less than the speed of sound, we use this relationship that the wavelength in front of the airplane would be equal to the speed of the source minus the speed of sound divided by the frequency of the source. So this is the same thing as the Doppler effect that we were discussing before. We expect that as long as we remain less than the speed of sound, then the waves are just simply compressed in front of the plane. But whenever the speed of the source is greater or equal to the speed of sound, then the wavelength goes to zero and the waves pile up in front of the plane. So the plane must exert force to compress the air in front of itself, and that compression of the air increases the air resistance, which is what actually leads to the sound barrier. So this is why it's so difficult to have something go faster than the speed of sound, because the faster it goes, the more the air is compressed in front of something like an airplane that's trying to break the sound barrier, which increases the air resistance. So the more thrust the airplane actually needs in order to move through that compressed air. So this is why it's difficult for the sound barrier to be broken. Now, the effect of traveling faster than the speed of sound leads to something called a shockwave. And a shockwave is where the circular waves interfere with each other. So as the source is moving in a straight line here, it emits a sound wave, and based upon the amount of time, that sound wave has time to spread out. So as it moves forward, that wave was generated less time in the past, so it's traveled out less distance. So that's why you get this cone effect here, because this point here is where the plane was originally, and then while it was moving to the second point, the wave had time to travel outward. Whereas at the second point, it's had less time to travel outward than compared to the first point once you get to the third point. So this is why you get this cone, because at each point emitted, the sound has had less time to travel outward. And along this cone is where you get constructive interference. So whenever you're hearing something like a sonic boom, you're actually getting the edge of the shock wave traveling over you. So because that's where the constructive interference is. When you're inside of this bubble here, you actually get a lot of destructive interference. So you're not hearing the sound as much as you would along the edge of the shock wave. And we can calculate the edge of the shock wave by analyzing how far the object has traveled forward in a certain period of time compared to how far the sound wave has traveled outward in the same time period. So I'm going to define an angle alpha here. So the sine of alpha, opposite over hypotenuse. So opposite here is going to be the distance that the sound wave has traveled, and the hypotenuse is going to be how far forward the source has traveled. So distance is velocity times time. So velocity of the sound wave times time, velocity of the source times time. So since we said the time is the same, we cancel them out. And we get that the sine of the angle that defines the shock wave is the speed of sound divided by the speed of the source. And the inverse of that is what we refer to as the Mach number. So Mach number is simply a statement of how many times faster the source is traveling compared to the speed of sound. Now remember, you do have to be careful about the speed of sound. It's not a constant like the speed of light. So it depends upon what substance you're traveling through as well as the temperature of that substance. So it's actually really hard to establish whether something has traveled faster than the speed of sound, because you have to figure out what the speed of sound is in that particular medium at that particular moment. So a number of years ago, somebody attempted to essentially skydive by going incredibly high up in the atmosphere in a special suit to personally go faster than the speed of sound, but it was very hard to establish whether that person succeeded, because high up in the atmosphere, the speed of sound is going to be different because of the different temperature and the different density of the atmosphere. So there's a lot of calculations that had to go to as exactly what the person's speed was at a particular moment and what the speed of sound was in the atmosphere at that particular position to see whether that person actually succeeded or not.